This week in class we're going to be looking at more time-varying voltages and also learn about capacitances and the charging and discharging of capacitors. We'll use these as examples of time-varying signals, time-varying voltages, and just get more experience using the oscilloscope. So we'll start off by looking at different periodic waves and learning how we can characterize periodic waves by determining their period, their frequency, and their amplitude. We'll then look at exponential functions that describe the charging and discharging of capacitors. And one final thing we'll do this week is talk about a combination of voltages. In this case, we're going to look at a DC voltage and a time-varying or an AC voltage added together and see how we can use capacitors to separate those signals. We see here three fairly commonly used time-varying periodic signals. And by periodic, we mean that the signal repeats itself every so often. And the length of time that it takes to repeat itself is known as the period. We're going to use the variable name capital T to represent the period. So a period is the length of time it takes to go from one point in the cycle all the way through to that same point again. Now obviously there's a number of different places that we can easily identify the periods. We can go from peak to peak or crest to crest. We can go from trough to trough. We can go from zero crossing to zero crossing, but we have to be careful which zero crossings we're going to. So we'll specify a negative going zero crossing, or a crossing that's going from the positive to the negative, going from positive to negative sign, as the negative going zero crossing and the positive going zero crossing. So we can also talk then about the period going from the negative going zero crossing to the negative going zero crossing, or from the positive going crossing to the positive going crossing. This waveform here is known as a sinusoidally varying waveform. A similar waveform, or another periodic waveform, is a square wave or a rectangular wave periodic waveform. In this case, we can measure the period from the negative going edge again to the negative going edge, or from the positive going edge to the positive going edge. And then this is known as a sawtooth waveform or a triangular shaped waveform. Once again, in this case, as these others, we'll talk about the period of the waveform as the length of time that it takes to repeat itself, and we'll call that capital T. Now another common way of describing these periodic waveforms is to refer to its frequency. Now the period T has the units of seconds per cycle. Frequency, that we'll use the letter F to represent, has the units of cycles per second. So we can look at these and see the relationship. Frequency is just equal to the inverse of the time, or of the period rather, and so we can say then that frequency is equal to 1 over cap T. So for example, if we had a circuit, or a waveform rather, that had a period of T equals 0.01 seconds, frequency would equal 1 over 0.01, or it would equal 100 cycles per second. And another name for cycles per second is the name Hertz, and it's abbreviated by the capital H, lowercase z. And Hertz is the name of a German physicist that was involved in the early work with sinusoidally varying electrical signals. The final signal parameter we're going to talk about is the amplitude of the time-varying signal. And we can talk about the amplitude either as the peak amplitude, which is the change or the height of the peak relative to zero. And so in this case, we would say that V, the peak voltage, would be 5 volts. Now we can also talk about the peak to peak voltage, which then specifies the total range that the waveform covers, and we refer to that as peak to peak, or V peak to peak, and in this case it would be 10 volts. Similarly here, the peak voltage here would be 1 volt, and the peak to peak voltage would be, it looks like about 70.75 volts here, and So in this, the peak voltage would be 0.75 volts, and the peak-to-peak voltage would be 1.5 volts. And down here, similarly, about 0.75 or 1.5 volts peak to peak. Another name that you'll hear used to describe these types of periodic waveforms are AC waveforms, or alternating current waveforms. And although they're not necessarily always currents, we can have AC voltages also. Generally speaking, when we're talking about AC, we'll be talking about sinusoidally varying waveforms or sinusoidally varying voltages. And the most common AC voltage out there is the voltage that you get out of a circuit or out of the outlet of the wall, which is oscillating at 60 cycles per second. So for the wall outlet, frequency is equal to 60 cycles per second, or 60 hertz. Its period then, T, would be 1 over 60 cycles per second. Its peak voltage, well, the amplitude of the voltage out of the wall is a little bit different. It's known as, we typically refer to it as its RMS voltage. So when we talk about 120 volts, that's the RMS voltage, which stands for root mean squared voltage. And it has to do with the average power in the voltage wave. And we'll talk more about it later, but suffice it to say that it's related to it's an average quantity that's related to the power of the voltage. And we'll learn more about that later again. But the peak voltage coming out of the wall socket is actually about 169 volts peak.